Okay, so here's what we were talking about last time. We were talking about partial derivatives. We talked about how to, what's the definition of a partial derivative? How do we denote it? How do you compute partial derivatives? All of which is really good news. This is all easy, right? And then how do you geometrically interpret partial derivatives, including second partials? So just real quick, I want to make a quick pitch for why partial derivatives are important. And I mentioned this at the start of the talk on partial derivatives, that as easy as they are to compute, it's just a really good idea to always write other derivatives, whatever they might be, in terms of partial derivatives, because then those are easy to compute. Right. So some examples of where partial derivatives come up as a really convenient tool. All of these are from physics. I don't know enough economics to show cool econ examples, but anyway, these are all from physics. So Laplace's equation. This is an equation that helps you understand what's called electric potential, sometimes called voltage. Right? If you arrange charged particles in some way, and you want to know, okay, well then how does that affect potential? It's kind of like if you were to arrange mass in some arrangement, you want to compute the corresponding gravitational potential. Right? Understand the gravitational field. So this is sort of an electric version of that. This is the equation that does that, and you'll notice that it involves partial derivatives. Okay. All right. If you want to understand how heat flows around, now y'all understand the sort of the simple rule of if you have a hot thing and a cold thing and you put them next to each other, then heat flows from the hot side to the cool side, right? But what if it's more complicated? What if you have hot heat here off center in an aquarium tank full of cold water? Well, that heat is going to it's not going to heat up this part of the tank at the same rate it's going to heat up this part of the tank right next to the heat, right? So how does the heat sort of flow through that aquarium? Well, it's a hard problem. This is how you write it, is the punchline. And notice, bunch of partial derivatives. If you want to understand how waves propagate, right? So, for example, nice still lake, you take a rock, you throw it in the middle of the lake, and it makes a splash, but then there's that wave emanating outward. How do you understand how that wave propagates? Right? Well, something called the wave equation. And again, it has to do with partial derivatives. And just real quick, this is a shorthand abbreviation for that we call the Laplacian operator. The Schrodinger Equation. I think a lot of y'all have heard of this probably. It's the one of the foundational equations of quantum mechanics. If you want to understand how mass works, right, at the very small scale. Well, it's Schrodinger's equation, and you'll notice that there's that Laplacian, which is made up of partial derivatives. So, tremendous amount of things that happen in the natural world are described by equations that are most conveniently written in terms of partial derivatives. Okay, all right. Yep.
Can you explain what the triangle is again?
Yeah, so this triangle thing is called the Laplacian operator. Here, let me connect it up here. It's the Laplacian operator because it's the operator that's in Laplace's equation. Yeah, it's just a shorthand. Mathematicians find it when they write the same thing over and over again a bunch of times, and it just gets old. And we make up. Yeah. Okay. Okay, so moving on, we're going to talk about increments and differentials. I hope y'all remember a lot of this from Calc 1. I think you probably do. Delta F, right? I mean, if you have some function and you're looking at the values of that function at, two nearby points, the difference in the value of the function at those 2 points, that's delta F, right? So anyway, we're going to refer to this as the increment. That's the terminology. There's this other similar but not the same thing called the differential. The differential of that function is not the change in the value of the function itself. It's the change in the value of the linear approximation to the function. So to make a picture that y'all, I'm sure, will all recall, let's see here. Let's make a little axis like this. And let's suppose we have some point here, x, and then nearby x plus delta x. right? And you can talk about a function. The function maybe is doing that, and you could say, okay, well, the value of the function there, the value of the function there. You could look at these two values. Right? That is the increment. Okay. The differential says, well, yeah, that's nice and all, but sometimes I can't compute these things, so we're going to look at the linear approximation, whose graph is this tangent line. Right, there's that tangent line. This is the graph of the linear approximation. The linear approximation's value is there. Next value is there, and you can look at that difference. That's df. Not to be confused with delta f there. Okay, so hope that rings a bell, right? And familiar notation. All right, so how do we do that in a multivariable context? Well, here's our linear approximation formula in the multivariable context. Now I'm changing the notation here a little bit. Let me come up and draw a picture. For one thing, I'm drawing a graph in the single variable context, and I don't really want to draw. I can't. It's hard, right, to draw a graph. I guess I'll give it a quick try, but this is going to be a significantly inferior picture, drawing a graph of a function and its linear approximation. But here we go. Whoops. So the function might be doing something kind of like this. Right? At some point down here in the domain, I'm going to call that point A, comma B. Right? And you can talk about the value of the function at that point. Sitting over that point, the function has some value. Oh, I didn't do a very good job with that. Let me, let's say it's like this. Okay. And then you can look at a nearby point in the domain. We'll call that nearby point x, comma y. This is another sort of, adapting another standard notation from Comp 1 classes. And that point, well, we can look on the graph, and there will be a value that's a little higher. Yeah. So here's your increment. Right, there's your delta f. The differential, just like it was in the single variable case, what we're going to do with the differential is we're going to just look at the linear approximation of the function instead of the function. In this graph context, we'll be drawing, therefore, the tangent plane, as that is the graph of the linear approximation. That tangent plane, now here's where the picture is going to be hard, right? I'm going to try to draw a plane tangent to the surface at that point. Problem, I haven't really drawn the surface at that point. You're going to have to kind of use your imagination, pretend like you can visualize that there's actually a surface in there that I could actually draw something tangent to, which there isn't, and I kind of sort of can. Here, graphs are great. Here I can draw the whole curve. You can totally see what's going on nearby there, right? So again, big limitation here, but forgive me for that, and here's my resulting. Let's see here if I can. Let's pretend that that's the tangent plane, kind of, tangent under that surface. You can kind of see it coming in, something like that, maybe. Okay, so the linear approximation, then, the value is going to be a little different at that other point. Of course, it's going to be the same at the approximating point, and coming in a little lower. This difference here, let me just do it over here where I have more space. That's df. Okay, so again, in purple we have the increment. In green we have the differential df. Everybody on board? Okay. By the way, over here in the domain, looking at how much the input has changed. Unsurprisingly, I hope, I'm going to call that dx. Right, and so we have in this picture now df, our linear approximation of the change in the output, and we have dx, our vector differential of the input, the change in my vector position in the domain. Okay. All right. So, now, reminder, here's our formula for the linear approximation. Okay. F of A, of course, is the same as L of A. The whole idea of a linear approximation is I sort of start at that same value. I could whip that over to the other side. That difference then is just L of X minus L of A. That difference is the differential. Right? What's left over after moving that over? Of course, you see I have this. And neat observation, just look at the way this is written down. It looks like a dot product. It's something times something plus something times something. And let's just capitalize on that and rewrite that for algebraic convenience. It's a dot product. Okay. And then you notice something else. This thing right here, x minus a, comma y minus b, that's exactly this vector. That is exactly our dx vector. Right, so I'm just going to rewrite that as x minus a, namely dx. And lo and behold, our equation has turned out to something pretty nice. Altogether then, here's a simple equation that relates input changes in the domain, dx, with output changes, our linear approximation of output changes in the target, df. Okay, now again, I remind you way back when, the very first thing we said when we started talking about derivatives is that derivatives, in some way or another, are a connection between, a relationship between, however you want to say it, input changes and output changes. And notice that's what this thing here is doing. This thing that, oh, by the way, I skipped over, this is just a notational, sorry about that, notational shorthand. This is called the gradient of f. It's just notation, terminology. That is the thing that you multiply by the input vector change to get the output vector change, or the output change. Yet this is playing the role of a derivative. And that's a huge observation. This is arguably why we care about this thing called the gradient. It's the relationship between input changes and output changes, at least in linear approximations. Is everybody on board? Does everybody see how nice that is, and how this dovetails perfectly with this point of view that we took on derivatives earlier? Okay, right. Okay, so again, make sure to remember the formula. Again, this gradient, it's just the other part of that dot. It's the other thing that was involved in this formula that came from the linear approximation. And as it turns out, kind of neat, it's just a vector consisting of the partial derivatives of the function. Okay. All right. Okay, so let me show you a quick numerical example, just computational example. And this is just quick for what it's worth. But so here we go. Let's suppose I wanted to compute this expression right here. It's completely intractable. Right? Taking a cube root, we don't really know how to take cube roots by hand exactly. I mean, there are algorithms that converge, but they're pretty weird. And plus, notice I also have to take a 100th root of e before I get to that cube root. So this is a nightmarishly inaccessible question. So what I'm going to notice is that this expression that we're interested in is the value of a certain function. It's the value of a certain function at a certain point. This is what I get when I plug in x equals 3.02, y equals 0.01. Right? You plug in that value of x and y into that purple function, and that's what we're trying to compute. So don't think of this as an algebraic expression. Think of this as a value of a certain function at a certain point. Okay, so rather than compute the value of the function, we're going to approximate the value of the function, and approximating functions is what this does, right? This gives you differentials. Differentials are approximations. They're approximations of how much did a function change. So this point that we're interested in, notice that, and by the way, I hope this is flashing you back to Calc 1, where you're evaluating a function at a point, but that point is near a convenient point, a really nice point. Right? That's what's going on here. This 3.02 0.01 is really close to 3, 0, much friendlier number. Right? And the differential of input there, so the dx is just 0.02, 0.01. Okay. So I'm just going to play the linear approximation game, and with that in mind, our differential computed by that formula. Right, let me do it like this. Computed by this formula. What is the gradient? Well, the gradient is just made up of the partial derivatives. I just have to take this function and compute a couple of partial derivatives of it. Partial derivatives, again, super easy. You get to use all your familiar rules: product rule, power rule, chain rule. You get to pretend like parts of it are constant, right? Partial derivatives are really nice. So take a couple of partial derivatives. Observe, as we already have, that dx is 0.02, 0.01. Of course, we're going to evaluate this gradient at the point in question. This gradient gets evaluated at a, so 3, 0. Lucky break, the arithmetic with 3, 0 works out really nicely. You end up needing to take a cube root of 8, which is 2. Right? So that was lucky. And as a result, this gradient turns out to be just that. You can then compute this dot product. Again, easy arithmetic. That dot product ends up being about that. And of course, there's a continuing fraction there, but we're just approximating here, so that's fine. Okay. All right. Now, don't forget that's the differential that we just computed. This is our differential. That's not our linear estimate of the function. The linear estimate of the function is what you get when you add that differential in to the starting value of the function, which, again, I refer you to the arithmetic. It's just 2, easy plug and chug. So add that into the original value of the function, and here is our linear approximation of the value of that function. And to show you how well this has worked, if you were to instead take that nasty expression and plug it into the calculator, you get this, and notice it's pretty close. Okay. All right. Okay, so this is really just a multivariable version, again, of problems that you saw in Calc 1. So note that strong connection. Note the differences. Okay. All right. Okay, so this next page of notes is a very, very summarized discussion of a complicated, substantial topic called differentiability. And we're just not going to be able to, in Math 212, to give it the amount of time that's really honestly due to it. So, so be it. I'm going to momentarily set aside part of what's on the notes, and then I'll come back to it. And that is defining what differentiability means. We'll come back to that in a moment. So momentarily, let me scratch that out, but we're going to unscratch it in a second. The reason that differentiability is important, I'm going to start with the end, right? So where's the punchline of this? Why do we care about differentiability? We care about differentiability because we need it to properly state a bunch of theorems that we're going to be using. Theorems have conditions, as y'all know, and you want the conditions to be strong enough that your theorem is actually true. That's always nice, right? But you also want your conditions to be no stronger than necessary, because the stronger your conditions are, the less broadly they apply. Right? So you don't want to state a theorem in unnecessarily strict terms. You want to state the theorem in exactly the appropriate level of strictness on its conditions. Okay, so the right answer for a lot of theorems is this thing called differentiability. That's hard to define. Okay. All right, so let me show you the workaround. The way that we're going to deal with this problem is to use a related notion called continuous differentiability. And continuous differentiability is easy to define. You need for all the partial derivatives to exist and to be continuous. I think the terminology here is extremely satisfying. Continuously differentiable, right? I mean, isn't this kind of what you would guess would be the definition of continuously differentiable? The only derivatives we know in relation to the word differentiable are partial derivatives. Continuously suggests that those derivatives should be continuous. So like I say, very believable. So the great news is that even though differentiability is really hard to define, and we're going to kind of do a poor job of that in this class, continuously differentiable is both easy to define, easy to check, and also implies differentiability. So that, in practice, that's how we're going to deal with differentiability in this class. You're going to check that a function is continuously differentiable by easy steps. Just compute the partials, right? That's hardly anything. And then observe that they're continuous. Practically everything is. Okay. All right. Okay, so like I say, in practice, that's how we're going to do it. Now, let's actually talk about differentiability. Like I say, differentiability is harder to define. Here's the definition, and this is in the book. Function's differentiable. If you can do this. So there needs to exist a vector called C that makes this multivariable limit equal to 0. So, why does this expression, why do we care about this expression? Very roughly, very approximately, where this expression comes from is that this is going to end up being that linear approximation. Side note, giving it all away, this is going to be the gradient vector if the function is differentiable. But anyway, that's, so that's going to be your linear approximation. That's your differential of the function. This here is the increment, you'll notice, of the function. And so what we have here in the numerator is simply error. That's all it is. It's the error in the linear approximation. So you need your error not only to approach 0, but even what we call relative error, even once you divide by the size of the change in the input. So you need that to approach 0. And roughly speaking, I mean, if your relative error approaches 0, in very broad terms, what this means is that your gradient's giving good approximations to how much the function's changing. Your differentials are good estimates. And notice I have this good in quotes. Right? So again, what does good mean? Good means this. And it's hard to write down. Okay. In geometric terms, it means that the graph of the function that you're trying to deal with has a what I'm going to call a good tangent plane. In other words, that there's not something really terribly wrong with, like, you could imagine if the graph had a corner in it, a piece of paper that's been folded and has a corner. That doesn't really have a good tangent plane. Right? What would be the tangent plane? It's just like with curves. There's no good tangent line to that curve at that point, right? So, if you try to make sense out of what you mean by a good tangent plane, well, honestly, what you end up writing down is this. And so the details of those discussions, why does good in both of these cases come out to meaning this? That's something we just really don't have time to flesh out. But I want y'all to know kind of what the punchline is. Differentiable means that differentials work well, and that the graph is kind of nice. Right? So very broad strokes. Okay, so remember, this is what you check. You then cite this theorem and say, ergo differentiable, in satisfying the conditions on a large number of theorems that we're going to actually compute a bunch of stuff with. So that's really the bottom line of what y'all need to know about differentiability. Okay, so moving along. So we're gonna venture into the chain rule now. We're not going to finish chain rule today, not by quite a bit. There's a lot to say about the chain rule. It's complicated in multivariable calculus. It's just a lot of stuff. But I want to get started, and I'm going to show you my first example of the chain rule with the kind of a reminder. Don't forget, we've already written down our differential. Here it is. The differential is just a dot product of the gradient with the input differential. Now I'm using different notation here. Previously I had written this was I had written as x minus a, right? And I had written this as y minus b. It's a little bit different notation, but that's all this is. This is just the differential, right? Specifically, where the value of the function I've given a name to. I'm calling it z. So notice that we have one output variable, two input variables. Thus, we have a function from R2 to R1. That's the context we've been considering. And now I want to precompose that, function of two variables. Z is a function of x and y. I'm going to precompose that with t. So, in other words, rather than just viewing z as being a function of x and y, end of story, let's say, well, hey, maybe x and y are functions of time. In other words, maybe I'm moving around through the xy plane. And as a result of x and y being functions of time, as x and y move around in the xy plane, well, that's going to make z move as well, right? So, altogether then, simply by making everything a function of time, I've got a couple other functions to think about here. I've got this curve. This is a parametric curve in the xy plane. X and y position, functions of time. It's a parametric curve. It's motion, right? And then I've also got this, the composition that is giving me the total output, z, as a function of time. Okay. So there's lots of functions whose derivatives we want to talk about and relate, and as you might sort of see coming, y'all remember the chain rule in single variable calculus. The chain rule in single variable calculus is about how do derivatives of compositions relate to the individual derivatives, right? And that's what we're going to do here. We're going to try to talk about what is dz dt, and how can I write that in terms of the partials of z with respect to x and y, and the derivatives of x and y with respect to t. Okay. And the good news is we're basically there already, at least in this case. Notice I can just take this thing here and then just divide by dt in all the terms, right? And lo and behold, we're kind of done. Right, there it is. We have here now dz dt, the derivative of that composition, right? And it's written in terms of the partial derivatives of z with respect to x and y, and the derivatives of x and y with respect to t. Good old same idea of the chain rule, composition broken down into individual derivatives. We just have a slightly different formula for it here. Comes straight out of the formula for the differential. Everybody happy with that so far? We're going to see a bunch of examples and developments. All right. Okay, so I want to give you a different point of view on this formula, how to think about where this formula comes from. I mean, there's something a little bit unsatisfying, if you will, about, well, take our existing formula for linear approximations and algebra, and there it is, right? Okay, it's kind of an algebraic argument. So here's more of an intuitive way to think about it. Let's draw these functions. I'm going to draw these functions sort of vertically now. The book does this sometimes, and in different books you'll see it, functions, compositions written vertically instead of horizontally. So let's do it this way. And notice that I have x and y, functions of t. Okay. And notice that I have z as a function of x and y. Okay, and let's consider the question of dz dt. As I make little changes in t, how's that going to cause changes in z? That's what a derivative is. Input changes cause output changes. What's that relationship? Okay. All right. Well, one step at a time. Let me tell you how z changes. Z changes because x changes. Right? If you want to know how much z is changing, take however much x changes and multiply by that partial derivative. That will, however much x is changing, that'll tell you the corresponding how much is z changing. Okay, but wait a minute, that wasn't the question. I don't want to know just how much does z change when x changes. I want to know how much does z change when t changes. Right? I'm interested in if t changes by a little bit. Well, the thing is, when t changes by a little bit, that causes x to change, and then, of course, that change in x will cause a change in z. So there's sort of a two-step process by which changes in t propagate, I'm going to say, propagate up through x to cause a change in z. Okay. And how much is going on here? Like if I change t by a little bit, how much does that change x? Well, that's what dx dt is. Okay, so altogether then, let's walk through this process of changes in t propagating through to become changes in z. However much t changes, you're going to multiply by dx dt to infer how much x changes. And having done that, you were then subsequently going to multiply by that partial derivative to get how much that change in x turns into a change in z. So altogether, you've multiplied by these two factors. You've multiplied by sort of both of these factors, and therefore altogether you've multiplied by that product. Everybody on board? Does that seem kind of plausible? Factors multiply for one thing. Okay. All right. But here's the thing. That's not the whole story. Right? That's part of the story. Yes, it is true that changes in x cause changes in z. But what about y? Z is a function of y too. If y changes, that's going to cause a change in z. And side note, y is changing. How do I know y is changing? Because t is changing. Y is a function of t. Right? So we've got a whole nother path along which changes can propagate. Changes in t cause changes in y, magnified by that factor. And then those changes in y cause changes in z, magnified by that factor. Altogether, then, you multiplied by these two factors, and therefore this product of factors. So this is a whole separate contribution to how much z is changing. Z is changing in two different ways. Partly because of x, partly because of y. And grand total, then, the total change is the sum of those two. I think that's really plausible. I think it's very sort of satisfying. Thinking in terms of just what the individual variables are doing. Something to chew on, something to digest. Now notice, it's just another way of thinking about this formula that we already got by a different argument, right? It's not like we need this point of view, but I think it's a nice, useful point of view. Okay. All right, so sometimes, by the way, my little shorthand for this is going to be that changes will propagate along paths, and I'm just going to write down a path as an arrow, and I'm going to say, and this is the term that corresponds to that path. And then, so this is shorthanding that, okay, well, dx dt, dz dx, those are the two factors inside of that path. Okay. Okay, so path gives term. right, let's do an example. So, say z is a function of x and y, like so. We talk about its partial derivatives. Suppose that x and y themselves are then functions of t. And again, this is just like our setup that we had on the previous page. Well, if x and y are functions of t, then I can talk about the derivatives of x and y with respect to t. Now, all the calculations that we've done down here, this is all just straightforward. Take the derivatives, product rule, chain rule, quotient rule, whatever. Power rule. Okay. So, but how do I combine this to ask the broader question of, now how though is z changing in terms of t? How do these functions compose? T is causing changes in x and y. X and y are causing changes in z. Altogether, what's dz dt? And copying just from the previous page, dz dt, this overall derivative here, well, there's the first term is the term that is propagation through x. And it's just the product of those two factors. That's propagation through x. And then the second term, well, this second term is propagation through y. Again, those derivatives we've already computed. And so there you go. Everybody see how that's just an immediate application of the chain rule? Okay. All right. Now I want to emphasize, I've discussed the following on the class webpage. This is a great specific example, so I want to go ahead and digress just a moment. So remember, when you get to an exam, on the exam, part of your job on the exam is to look at the question and infer reasonably from the question, what is the intended, what am I asking you to demonstrate? Right? And I don't want to always give away the game and say, by the way, here's the method you have to use, because that gives away the game. That then you don't have to then think about and do the analysis and diagnose. Oh, here's the method I should use. Right? So I want you to do that. Your job on an exam is to infer correctly what Math 212 material is this question about. Right, and then to demonstrate what I'm asking for. So along those lines, if I were to ask you this question, you should do something like this, right? Don't take this formula for x and stick it into there, and this formula for y and stick it into there, and multiply it all out and get this great big function where z is explicitly a function of t. And then just use Calc 1. I mean, that would get you to the answer. Yeah. Right? But it completely bypasses Math 212 material. Right? So it completely bypasses the purpose of the question. So don't do that. That would be a very little partial credit type of a situation. Does that make sense? Does everybody understand my motivation for this? Right? Now, a way to get around this is I could just write questions where stuff like this is impossible. And sometimes I do. But it tends to be the case, to be honest, that when I write questions that make this impossible, defending, therefore, my intentions on the exam, they tend to be harder questions, right? So it just seems pointless for me to go out of my way to make a certain technique impossible when I can just simply disallow it. Right? So I'm disallowing in Math 212 this plug in and brute force turn this into a Calc 1 problem. So does that make sense to everybody? Any questions about that policy? And then, by the way, likewise in other parts of the course, you're supposed to interpret questions as opportunities for you to demonstrate Math 212 proficiency specifically. And, give me what I want. Okay. All right. Oh, yeah. Mm-hmm.
Is there like a formal way to write that x and y are explicitly functions of t?
Oh, yeah, you can just write, x equals x of t. This would be taken as x is a function of t. Yep. Right. Was there another? Yeah.
So you're saying you just don't want us to use this technique?
No, I want you to use this technique, and right, because this is Math 212 material, right? What I don't want you to do is bypass this completely by plugging these into there and writing, z explicitly as a function of t, in great gory detail, and then just taking a deep breath and powering through it with Calc 1 methods, right? That's not the point of the question. It's got nothing to do with multivariable calculus. So that would be inappropriate, right? Yeah. Okay. So now, how do we evaluate this? Suppose I want to compute this function. This derivative. I want to compute that specifically at pi over 6. Notice that this pi over 6, that's to be interpreted as a value of t, because we're talking about dz dt, therefore as a function of t, so pi over 6 is t. Right? And that being the case, now, a couple of things that you could do. You could plug that into there, as needed. And you could say, oh, yikes, well then I've also got to, I've got to deal with this x. Well, x, I'm going to have to rewrite x as cosine t and stick that in there, and also there. And then I'm going to have to take this formula for y. Yikes, wrong color. This formula for y, I'm going to have to plug that in to there and there, and expand out and get this enormous function of t for, that gives us dz dt, and then plug in pi over 6. Right, so you could do that, I suppose, but a convenient shortcut, and I think especially in this case, is notice that if t is pi over 6, you can plug that into there, and then just once as needed, just the one time, compute what x and y are. And then just plug those in. I mean, that's x and y, so just plug them in. And that's what I've done here, you noticed. So you don't have to rewrite everything in terms of t, unless there's a good reason for it, but don't have to. Everybody happy? There's a single variable analog of this. Y'all have seen this kind of situation before in Calc 1 context as well. Okay. Right. What happens if you have more variables? And by the way, I'm calling these intermediate variables. Intermediate in the sense that, you've got your sort of first variable and there's sort of last variable, and what I'm referring to as the y's are the ones that in between, right? Intermediate between x and z in this case. What if you have more than 2? And the idea is really analogous to what we did here. The big idea back here was that for every path, there's a corresponding term, right? For every path through which changes can propagate, corresponding term. Well, if you have more intermediate variables, you've just got more paths. So for that first path, going through y1, here is the what I'm going to call the y1 term in the chain rule. Notice partial of y1 with respect to x, partial of z with respect to y1. Right? So again, each path gives you a term. Each term has 2 factors. Okay. So likewise, there's a y2 path and therefore a y2 term, etc., 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 etc. Right? You keep getting extra terms for each one of the intermediate variables, and then finally, lastly, that last path through yn gives you the last term, the yn term. Totally analogous intuition. Okay. All right. Is everybody happy with this? Any questions on that? Okay, now here's a weird question. What if we have other input variables down here? How's that going to change things, right? Previously, we considered only one input variable, And we've talked about, just momentarily ago, multiple intermediate variables, and that's nice and all, but what if I have lots of initial variables? Well, it changes the question that you can ask. You can no longer ask for what is dz dxi, because z is not a function of just xi in the composition. In that composition, z is a function of a bunch of different variables. Right, so what you could reasonably ask is, what's the partial derivative? Namely, let's suppose I hold all of this stuff constant. And then I could reasonably ask in this composition, what's the partial derivative of z with respect to xi? That's a reasonable question you can ask. Okay, so that said, if I want to know that partial derivative, I am holding all of these other variables constant. Then notice that as I look at these paths, let's look at this y1 path, you might say. How does y1 change as xi changes? Well, keep in mind we're holding all these other variables constant. And so that is just the partial derivative of y1 with respect to xi. So having all these other extra variables restricts us to asking partial derivative questions, which basically says, ignore all those extra variables. Slightly shorter, if you have extra variables in the domain, ignore them. Right? And just recognize that we now have to call these partial derivatives instead of, derivatives. Okay. Punchline, it doesn't change the structure of the answer at all. It's still a bunch of different paths, each one of which gives you a corresponding term in a summation. Okay. All right. Here's one more question. This is probably going to be our last one for today. But suppose you are given this. So I've got a formula for W, a formula for P, a formula for Q, a formula for C. And we've been asked to compute a partial derivative, partial of W with respect to Y. Oh gosh. Which ones do you put where? And how does this get organized? Which way is up? Right? Just make sure to be careful before you actually start writing down the chain rule. Look at what you're given and think about what that tells you about which functions or which variables are functions of which other variables. So it usually will fall into place pretty straightforward. So, for example, this is telling you W is a function of P, Q, and C. So, okay, fine. Then let's indicate that in a little diagram for ourselves. By the way, notice the diagram was not given. This is something I'm going to construct for my selfish purposes, right? I don't want to do this sans diagram. I need the diagram to help me see what's going on and which variables are intermediate variables, and I need a picture, right? So give yourself that picture. Draw this diagram for yourself. W is a function of P, Q, and C. Put that on your diagram. And you can see right here, P, Q, and C are all functions of X and Y. And put that on your diagram. And now we're nice and organized, right? So the question of, what's the partial of W with respect to Y? Well, there's W. Here's Y. Look at this. There is this other variable over here. Well, I'm taking a partial derivative of W with respect to Y, so the implied question then must be that we're holding X constant. And with that in mind, this picture having been made up, look, we've got three different paths. There's the P path, giving you the P term. There's the Q path, giving you the Q term. And there's the C path, giving you the C term. Right? So 3 paths, 3 terms, write down the factors correspondingly. And then it's just some real easy partial derivatives to compute. We've got explicit formulas here, so all these partials are easy to do. Right? And you plug in and simplify, and there's your answer. Yeah. Okay. The purpose of this example was to emphasize how important it is to make yourself a little diagram like that. Okay. And perfect timing. We're out of time, so we will pick up here on Friday. Y'all have a good day.